Okay, so we're live on everything we're supposed to be live on.
Nice, thanks. I'll start in just a few seconds.
Morning.
So hi everyone, welcome back to this series of lectures on the statistical mechanics of disordered systems. Let me remind you that we are talking about a problem of statistical inference where we observe a noisy version of a rank 1 matrix. In this rank 1 matrix, we write it as x bar transpose, and x bar is a vector of n components, and they are IID bounded random variables. And the law of this thing, we write Pn. And we observe this multiplied by some factor that depends on t, plus a noise which we call W. Okay, and we discussed last time that in order to analyze this model, it's going to be useful to consider a broader setting in which we observe not only this, but also the simply a noisy version of x bar. Okay, and this was square root of 2h x bar plus a noise, and this new noise we call W. We call Z. Sorry. Okay, I'm just going to slightly change some setting. So yeah, and then when we write the associated Gibbs measure, when we write the conditional law of x bar given these observations, we observe that it has the structure of a Gibbs measure, and the associated energy function we called Hn of t, h, and x, and I rewrote it here on the slide. So initially we were writing it in terms of these observations, which we were denoting y and y tilde. But here I rewrote them explicitly in terms of w and x bar. Okay, so this is the formula for Hn. And I imagine that it's a little bit intimidating because there are 6 terms. But I strongly encourage you to think that it's really these terms which are important and which look like the spin glass terms. And the other terms, they are around so that this inference structure is preserved. So this ensures that this Gibbs measure is actually the conditional law of x bar given y. And we've seen last time one property which derives from the fact that this Gibbs measure is a conditional law, and it is the I get some noise. Yes. All right.
Okay.
Thanks. Yeah, and the fact that this is a conditional law gives us a crucial property which we call Nishimori property. So, for instance, if we compute the expectation, okay, so maybe I should back up a little bit. So we'll see later what this Nishimori is again. But let me just say one more time the setting. So if you're maybe confused about all the variables that are around, so let me remind ourselves what they are. So there is x bar, w, and z, which are given in our problem. And for each realization of x bar, w, and z, we can define this bracket thing, this bracket notation. Okay, and we can take averages of some new random variable, which we denote by x. Okay, so this bracket thing is defined for each realization of w, x bar, and z. and therefore it's a random thing, and we can take the expectation of that thing. And what we've seen is that that expression is the same as the one where we put a bar. And we had something similar when we put more replicas, more copies of X inside this bracket. And this was the Nishimori property. All right, and finally, the last thing we did last time is discuss the Gaussian integration by parts. And so I wrote down 3 formulas, but I'm only going to recall the first one. And it's displayed here. So Z is the Gaussian noise. This is some arbitrary function of X and X bar. And we saw that this expression can be rewritten in the following form. Okay? Something that does not involve any Z anymore. Okay. Are there questions on this? All right, so how are we going to study this measure? Well, we're going to approach this as we approach the Curie-Weiss problems. That is, we're going to focus on the free energy. And the free energy, or at least what plays the role of the free energy. So I'm not totally sure if I have defined it properly last time. I think I briefly mentioned it, but let me rewrite it. It's going to be 1/n, the log of the integral of this exponential of this energy function, Hn. dPn of x. Okay, Pn is the law of x bar. Okay, and remember that inside the Hn, there is some x bar and W and Z hidden. So this is a random quantity. So we can also define the average of this quantity. And this average I'm going to denote Fn bar. Oops. Okay, so this is unlike the Curie-Weiss case. In the Curie-Weiss case, the free energy was deterministic, but now we are finally really dealing with a disordered model. So the free energy as defined in the first line is still random, and we can take its expectation with respect to W, X bar, and Z. Okay. And as for Curie-Weiss, our approach to trying to identify the limit free energy will be to try to look for a partial differential equation satisfied by this object. So what I'm going to do is try to compute the derivatives of this thing and see what happens. Okay, so I'm going to start with trying to compute the derivative with respect to H. So this is the function we try to differentiate. Inside here, there is an H. And so, we look at where H appears inside the definition. It appears in these slots. So as usual, when we differentiate this free energy, what we're going to get is some Gibbs measure of something. So we're going to get this angular bracket of 1/√2h x dot z plus 2x dot x bar minus x squared, and that's it. Don't need to. Okay. Yeah, the large deviation approach is not available because I don't know on what I can do the large deviation. I'm not sure exactly how to best explain it, but in the case of Curie-Weiss, everything was a function of 1/n sum of sigma I, and this I can produce a nice large deviation theory of, but here things don't appear as nicely, and there's no, at least I don't see any clear way to use the large deviation approach. Yeah, so okay, so I want to massage this term a little bit. The first thing I want to do is there is a z, and I have a technique to get rid of the z, which is displayed in the first line on the slide. So I'm going to do this Gaussian integration by parts to get rid of the z. Okay, but this I can only do if I also take the average outside. Huh? But I'm going to do that as well. Okay, so in the next line, I'm going to write dh of fn bar. Okay, so this is with the expectation over the entire randomness. And so I'm going to get x dot x minus x prime plus 2 x dot x bar minus x squared. Okay, and now we see some simplification. Here we get x squared minus x squared, so the x squared disappears. And this property of Nishimori tells us that when we compute the expectation of x dot x prime, it's the same as the expectation of x dot x bar. Okay, so I have 2 times x dot x bar here and minus 1 time is displayed. So overall, there remains exactly one of these guys. Okay, so the derivative here is expectation. Oh, there's a 1 over n I forgot in front. Sorry about that. You know, which just comes from here. There's a 1 over n here, which I had forgotten. Okay, so thanks to this Nishimori property, I can express this derivative using only one extra random variable in this bracket, not 2 as we could have. You know, initially I had 2 of these variables, like x and x prime, but I can simplify it and only use x. And if I try to compute the derivative in t, essentially exactly the same will happen. So let's do this. dt fn will be 1 over n. Okay, let me display the energy again. So it's here on top. So I'll have, okay, so bracket 1 over square root of 2tn w dot, or maybe I'll try to use the same, x star dot w plus 2 over n x star dot x bar star. So I'm rewriting this is an equivalent expression to this one. Just I want to display really very explicitly that it's exactly the same structure as when we differentiate in H. So instead of writing this, I reshuffle the scalar product and I write it like this, 2 over n, like this. And then the last term is minus. So I could write x to the 4, but I'm going to fancy to write it as x star squared. I do this because I want to display that it's really exactly the same structure as here. See, the only difference is that whenever you had an x, now you have x star, x bar, x star, etc. And the noise z is replaced by w, but otherwise it's exactly the same. So I have not explained explicitly. No, I have not given you a formula for the Gaussian integration by parts with respect to w, but it's going to work exactly the same way. Okay, when I take this average outside, I'll get, okay, so let me write this, dt fn bar. I'm going to get 1 over n times bracket 1 over n x star x star minus x prime star plus blah blah blah. Okay, the rest is unchanged. Yes, thanks for the comment in the chat. I had forgotten this one over n. Okay, and so exactly the same simplification can be carried in this case as well. And we get that this is 1 over n squared x star dot x bar star, which if I want, I can rewrite as 1 over n squared. Oh, I forgot the expectation here. X dot x bar squared. Okay, so the I hope this looks promising to you, eh? Because if you look at the derivative with respect to h, or that with respect to t, one is the square of the other, just like what we got when we were dealing with the standard Curie-Weiss case. So it's quite a remarkable phenomenon that essentially we are dealing with the same equation as for the standard Curie-Weiss case. Let me write this. So dt fn bar minus dh fn bar squared. This is the expectation of x dot x bar divided by n squared minus the expectation then squared. So in other words, it's the variance of this x dot x bar divided by n. Okay, so this gives us hope that, let me write this. Converges to the solution to the equation to the following equation. Okay, and that's what we are going to justify indeed. And another thing which is as in the Curie-Weiss case is that we can compute when we set t equals 0, we can compute this quantity explicitly, and in fact it does not depend on n. So let me explain that as well. So as in Curie-Weiss, let's say recalling that or writing. Remember that here we assume that x bar is a vector of IID random variables, so its law is a tensor product, an n-fold tensor product of a given measure. So I'm going to write it, it's just P1 tensorized n times. So when I set t equals 0, I have that fn bar of 0h is 1 over n log, oops, I forgot the expectation of the log. And let me rewrite explicitly what that is. So square root of 2h x dot z minus 2h x dot x bar plus h x squared dpn of x. And you see that everything can be factored. Like inside the exponential, you can write things component by component. For instance, x dot z, you can write it as sum of xi zi. This you can write as sum of xi x bar I. This is sum of xi squared. So you can really, decompose, it's really a sum over the indices of a given term. So you can write the exponential of the sum as a product of exponentials. Then because the measure is also a product, you can just rewrite this as just a product of all the integrals. And when you take the log, you get the sum of the logs of all the integrals. And when you get the expectation, it's all collapsing into a single, the same computation done n times. So overall, this is exactly the same as f bar 1 of 0h, which we can write explicitly. It's just the same expression where we set n equal to 1. So technically, there's only one, in terms of the description of the limit, there's only one difference with what we have seen with query Weiss, which is that in our problem definition, we are restricted to h non-negative. Okay, so only slight difference. But we'll see that this can be dealt with rather easily by just doing some mirror symmetry. So this is a particular case of the fact that the model is not complicated. In general, we do need to deal with the boundary condition, but this is also not particularly complex. Okay, so we're in good shape. Except we need to verify that our procedure for solving the query Weiss model can be extended to this case, which is not obvious a priori. But at least we have a relatively clear roadmap for what we should try to do. Does that make sense? So the goal is to identify this limit for energy. And like with query Weiss, if we manage to do this, we're going to learn useful information about the problem, because as for query Weiss, maybe what we really care the most is the behavior of the derivatives. Remember when we were discussing the minimal mean square error, we saw that it boils down to understanding this quantity, or maybe this quantity. But if I know that Fn converges to F, and as I'm going to discuss just next, I'm going to say that Fn bar is convex. So we are going to be able to deduce convergence of the derivatives at every point of differentiability of the limit, as before. Okay, and this will allow us to identify the minimal mean square error, which is the task we set ourselves to perform. Does that make sense? So really the main difficulty is to identify this limit for energy. And yeah, as a first step, let me state that this Fn bar function is indeed convex. So let's say proposition. So I'm going to explicitly write that it's a statement about joint convexity. So it's a statement about Fn bar. Yeah, I don't say that Fn is convex, just Fn bar. So yeah, I was debating whether or not I display some aspects of the proof of this, but I think I will perhaps not do it, because in the statement just after, we're going to do computations which are very similar. So let me give you some hints, let's say, of the proof. I mean, it's not. It's just you differentiate one more time. Okay, so let me just write proof idea. or at least why this should be plausible, at least. So if I start with, we've seen that this first derivative is giving us in some sense, the correlation or the alignment between x and x bar. So, and in fact, the larger it is, the smaller is the minimal mean square error. And so it sounds extremely plausible that if we increase the signal to noise ratio, so if I increase h, then I will be able to learn more about x bar, and therefore I will make a smaller error. And in other words, I will have this quantity be larger. Okay, x and x bar will be better aligned. So at least when we see this formula, it sounds extremely plausible that this quantity is increasing as a function of h. And when I say increasing, I mean I should say non-decreasing, but I dislike saying this, so I say increasing. If I want to specify strictly increasing, I say strictly increasing. Okay, and then once you believe that this is plausible, you just do the computation. Okay, so it's a computation similar to some we have done before. We write explicitly the Gibbs measure and we differentiate, and we see some correlation appearing, and we just try to keep track of the terms. So in the handwritten notes, there is a proof that indeed, if we differentiate twice, this is non-negative. And in the problem set number 8, problem set number 8 is about completing the proof of this proposition. So, but in fact, when you differentiate in T, it's exactly the same structure again. Just as we discussed, when you differentiate in T, the only thing that changes is that you replace all of the x's by xx transpose, all of the x bar by x bar transpose, etc. So it's really, if you look at the notes to get this result, then it's not difficult to see that the same non-negative thing will be true for if we differentiate twice with respect to T. The handwritten notes, yeah, sorry, I call them handwritten. I mean the notes that are in the Dropbox. Yeah, last time I missed, someone was confused by this. So yeah, I'm not giving a name, I'm saying it's handwritten. Sorry about that. Yes, so we see that the second derivative is non-negative in these two directions. So it's not enough to conclude that it's jointly convex, but then if you try to do the same thing in an oblique direction, when you differentiate in a direction which is having a little bit of h and a little bit of t, then it's again exactly the same structure. And so in fact, you can check that all of the oblique second derivatives are non-negative. And that is a proof of joint convexity. And the structure is again exactly the same. You just replace x by some combination of x and xx transpose. So yeah, so I'm going to have ultimately decided that I'm going to skip this argument. All right, and I want to instead focus on what is really at least one of the key ingredients towards the proof, which is to identify some way to say that this variance on the right-hand side relates to things which we can hope to control. Like with Curie-Weiss, we had seen that the variance is related to the second derivative of Fn, and there was this 1 over n in front, and we leverage on this 1 over n. So here I would like to identify something similar. So I'll also recall that the first derivative is non-negative. This is convenient. I said that our problem is restricted to H non-negative. And so in order to say that things are fine, it's convenient to know that the derivative is non-negative. But okay, let's not worry too much about this part. And the important part of the statement is the following. So here is the thing that we want to control. Okay, it's a variance, so it's clear it's non-negative. But the important part is that it's bounded by 1 over n times the second derivative of fn bar. This is exactly like in Curie-Weiss, the standard Curie-Weiss. But there's an extra term, which is the expectation of the difference between the derivatives of fn and fn bar squared. So this surely could not be part of Curie-Weiss, because in Curie-Weiss, fn is deterministic. But in this context where we really deal with a disordered model, we see a new error term, which involves, in some sense, the fluctuations of fn. Okay? In fact, the fluctuations of the derivative of fn. Okay, does the statement make sense? I don't write, but I mean that everything is computed at a given point. Okay? So I could write of th everywhere. Okay. Okay, so this is what I want us to prove today, and this I'm going to prove carefully. All right, so let's first settle this question about the derivative being non-negative. So this guy we said is the expectation of x dot x bar. And I'm going to use Nishimori again to make it look more symmetric. So I can also write it like this, x dot x prime. And this we have seen is a square. Let me remind you of this. This I can rewrite like this. So it's a square, so it's clearly non-negative. Okay, so that proves the non-negative part. And now for the approximate Hamilton-Jacobi equation. So with what we have seen, recall also, this is the variance of that quantity. Okay, so it's a variance, so it's non-negative. And now I want to say it's bounded from above by something that involves the second derivative and something that involves these fluctuations of the derivative of fn. Okay, so in order to do that, I'm going to introduce some notation. So define, I'm going to write it hn prime of h and x it's that thing that we got when we differentiated in H before taking this global average. So it's 1 over square root of 2h x dot z plus 2 x dot x bar minus x squared. Okay, it's convenient to focus on this quantity because this is really more directly what we get when we differentiate. Let me display it one more time. When we started the computation of the derivative, we got this. Okay, and so I give a name to this guy. Okay, and we've seen that after we take this global average, this global average is the same as the average of x dot x bar, but a priori, the quantities themselves are different. It's only after we average over everything that they have the same expectation. Okay, so in some sense they are related, but they are not the same. Okay, and what I'm going to claim is that it's actually more direct to understand the control of the fluctuations of this guy. And once we understand the fluctuation of this guy, we're going to say that these control the fluctuations of this term. Okay, so this is the plan. So yeah, maybe I'm going to again recall some of these calculations of above. So recall also dt of fn, sorry, dh of fn is the bracket of hn prime divided by n. And if I average over all randomness, then this has the same expectation as x dot x bar. Okay, and so in truth, here I want to control the fluctuations of x dot x bar. But first of all, I'm going to talk about the fluctuations of hn prime. And because they have some sort of tight relations like this, I mean, like they have some sort of relation, the things ultimately will wrap up nicely. So the argument is decomposed into 2 steps. The first step is to say that indeed the variance of this guy is controlled by the variance of hn prime. And the second step is to show that the variance of hn prime okay, and I have a 1 over n squared in front. That this guy is indeed bounded by the quantities that were announced in the statement. That's like 1 over n, the second derivative, plus the difference of the fluctuations of the derivative. Okay. So do everyone agree that if we have these 2 parts, then the proof is over? Okay, because we plug in, we can just chain these 2 inequalities so that we get an estimate of this in terms of this. And so then we plug in this formula and we are done. Sounds right? All right, so maybe I start with 2. Yes. So we have these 2 levels of randomness, and so we can decompose the variance into 2 pieces. It's a bit like if you want, it's like a martingale. Okay, let me write it down and then I explain. Okay, this is an equivalent way to write this term. It's the variance of Hn prime. This I claim is equal to the variance of Hn prime with frozen extraneous disorder, like the variance only with respect to the bracket, which we then average, plus the variance of this bracketing. How am I going to write this? Okay. This you can verify by hand, or you can also imagine that it's you have a 3-step martingale, and you know this is a this is your first increment of the martingale, the second and the third, and you decompose the increment into 2 bits. Well, anyway, this you can verify by hand explicitly. Okay. And you know, if you don't like it, you can also write smaller than or equal to and put some factors of 2 on the right hand side, and you will just lose the factors of 2. So we don't need to worry about this identity. Okay, you can always do an inequality. All right. And so I claim that each of these terms will give us one of these terms above. So it's easiest to see this one, because recall that here is the relationship between the derivative and Hn prime. Okay, DHFN is the bracket of Hn prime up to a factor of 1 over n. So this guy is n times DHFN, and this guy is the expectation of it. Okay, so no mystery about this part. We have already found the difference. You know, this term with the fluctuations of the derivative is already on the right hand side. Okay, so now there remains to see this term, and this one, on the other hand, is going to come just like with Curie Weiss, because when we have this free energy and we differentiate twice, we're going to be computing the variance of something, and precisely this Hn part. Okay, so it's not completely exact. There's a little twist, but it's almost true. So let me explain this. Yes, so if I write explicitly this expression, it's this integral of the exponential okay, that's what it is. And so if I differentiate in H this guy a second time, well, as before, as for query Weiss, what will happen is that another Hn prime term will pop out. And I will have then Hn prime squared, and then computed under the Gibbs measure. Now, it's not the only place where H appears. H also appears here. And here it's going to give me the twice the mean value of Hn prime under the Gibbs measure. So let me write this down. So dH2 Fn is going to be 1 over n Hn prime squared minus 1 over n Hn prime and then squared. Okay, so there's only one little twist, which is that because I put square roots of h instead of writing just h somewhere, in fact, there's still some h also hidden inside the definition of Hn prime. So I also have to remember to differentiate this guy. Okay, remember this definition is 1 over square root of 2h times x scalar z, and then terms that don't depend on h. So I get minus, so I differentiate this term, so I get h to the 3 halves times this, times this x dot z guy. Okay, and so when I now take the global average, like the E average, I'm going to obtain this term will look the way I want, and then there's just this little extra bit which I'm going to deal with. Let me write this. So dH2 Fn bar is 1 over n expectation of Hn prime minus Hn prime squared minus 1 over 2h to the 3 halves expectation of x dot z. And now I can use Gaussian integration by parts here. So let me just erase this and replace by what that gives. And this gives x minus x prime. Yeah, and I should cancel 2h. So I remove the 3 halves here. And this is expectation of x squared minus, x squared. So this is non-negative. So conclusion is that dH2 Fn bar that doesn't seem to be the way I want. Confused by something. Okay, I was supposed to end up with Yeah, I have a sign. I think I have a sign error somewhere. So let me. I wanted to get this inequality, and it's a good time for a break because I'm going to chase my sign error. So yeah, let's take a 10-minute break, and I'm going to think about my sign error. Worst case scenario, we can just keep an error term here, and it will be harmless anyway. But it's kind of cleaner if I can just discard it. That's true. Thanks for the comment. Yeah, so I was saying that I'm going to just discard I'm going to keep this extra term, which I was hoping to dismiss. But later in the proof, I'm going to find a term like this, which will help me to compensate. And so I have to amend the intermediate claims, but I don't have to amend the final statement. So here there will be a plus 1 over 2h n square expectation of x square. And here I'm going to add a minus 1 over 2h n square expectation of x squared. Sorry about that. I have forgotten about this annoying term. I thought I could just dismiss it. But you see, it's small anyway. You know, there's it's over the 1 over n. So, okay, when h is small, it gets maybe we're worried, but overall, you know, it's not going to actually pose problems.
But in the chain inequality, they will disappear also. When you combine the two inequalities, this term will disappear.
That's right. Yeah. So now I inserted it in a way that it disappears, right? Maybe it's cleanest if I move this guy. Oops. Let me move this guy here, and I put a minus, and I just insert it here, so that we see the chaining is still valid. Does that make sense?
Yes.
So yeah, the story was cleaner without this term, but unfortunately it's not true. So I have to keep it.
It seems a very long calculation, right?
Oh, and you haven't done we haven't finished it yet. Okay, I'll go and take some drop of water and be done. Okay, so let me summarize where we're standing so far. So far it's not so long, I think. So far it's okay. Now the computation is going to occur. But you know, so far we started from this observation. Okay, the equation, the guy on the right hand side is a variance. And we said, okay, we're going to decompose the variance into two parts. This is a decomposition of the variance into two parts. And the first part, we just observe that it's the fluctuations of the derivative of Fn. So it gives us one of the terms in the final result. And now we just have to deal with the second part. And yeah, and essentially, like, you know, it's okay. So So yeah, I said it wrong. Yeah, so let me restart. So on the right hand side we have this variance. Now, okay, I claim it's nicer to think first about the variance of Hn prime. And there is a clear relationship between Hn prime and x dot x bar because, well, for instance, we have this relation, and Hn prime is what we get when we differentiate with respect to H. So it makes sense to think about the fluctuations of Hn prime first of all. And when we observe the fluctuations of Hn prime, we do this variance decomposition. There are two terms. The first term is just that. Okay, one of the terms is just that. And the other term is the second derivative. This is just like with Curie Weiss. Okay, and there's just, it so happens that there's this extra annoying term. But this is because, okay, you know, I've put some square root in some place and it creates some little spurious term. But in any case, it's small. And in fact, in our context, it even compensates nicely with another term later. So we will not even notice it in the end. But even if we had to keep it around, it's a small term. So let's not worry about this. So I think so far the strategy is very reasonable. Like, it's as in Curie Weiss, except there's extra randomness, and so this term has shown up as well. Now, indeed, some kind of hard calculation is going to come, and it's when we try to verify this part. Okay, so maybe the proof of this will be the longest calculation that happens during this class. So let's prepare for it. It's not going to be horrible. We're going to do it, but it's going to be a bit long. Not too long. It's not so bad. So first of all, we've said that this guy and this guy are the same. Okay. Remember, it's written here. So in fact, the whole point is just to verify that when we compute the second moment, there is a relationship between the second moments of these two guys. Okay. This is what we want to do. And you know, when we compute the first moment, it's a direct equality thing. And we use Nishimori in some place and it worked out. It's kind of plausible that when we compute the second moment, the two things will still be very related, except maybe, you know, slightly twisted, but still with a close relationship. And you know, we have to uncover what is this you know, slightly twisted thing that I'm waving my hands around. So that's the computation I'm going to do now. Does that make sense? So all we need to do now is observe that when I compute the expectation of the square of Hn prime, it's larger than or equal to this guy plus this spurious term, which I just carry around, and which is not going to annoy us. Okay, and once we have done that, we have finished the proof. Good. So I'm going to try to massage this term just, you know, in the same way that we played around with Gaussian integration by parts, and we wrote this like this. I'm going to do the same with Hn prime squared instead of just Hn prime. So of course, you know, there's a square, so it's going to be a little bit more involved. But okay, it's not going to be a catastrophe either. So we are ready? So all that is left to do is to estimate the expectation of Hn prime squared from below. All right, so let's do this. good time to rewrite what is the definition. So 1 over code of 2h x dot z plus 2 times x dot x bar minus x squared. Everything squared. Okay, and now I just expand the square and see what happens. So you know the main thing that we need to do is try to use Gaussian integration by parts and replace z by x and x prime things. Okay, so that's what we're gonna do. So maybe I'm going to expand the square around the focusing on this z term. I'm going to write first the square term. Then the cross product. And then the square of the last guy. Okay, so far so good. And now I'm going to use our Gaussian integration by parts lemma to get rid of all the z's. Okay, so you remember the first term we had I have not recalled it today, but we have seen last time a formula also for computing using the Gaussian integration by parts for something which is of the form z dot some function everything squared. And the statement was that there are two terms. The first term is as if you freeze, you think of the square as being the multiplication of two copies, and you freeze one of the z's, and you pretend it's just like normal Gaussian integration by parts. So in this case, we're going to get 1 over square root of 2h. So one of the z's is frozen, and then I apply normal Gaussian integration by parts, so I get this x minus x prime term instead of the z. And also the square root of 2h is appearing. So that's why now I have only one over square root of 2h. And then there's this extra guy, and this extra guy, it was, so you know, if we were computing z dot some function g, everything squared, this extra guy was the expectation of g squared. So here it's going to be 1 over 2h times expectation of x squared. Okay, and this is the extra guy that I was annoyed with during the break. Okay, so it's already here. I don't need to worry about it. Okay, you know, recall that I want to lower bound this, and I had to discover this extra annoying term. So it's here, so no problem. Okay, and then the other terms. So plus, oops. Okay, so maybe let me just not touch the other terms for now. So there are, you know, the other terms are these and these. And now I'm going to do one more Gaussian integration by parts to get rid of the z's which are here and in this last term. Just this, so equals expectation of. And now, just one thing we have to remember is that now the function that's dotted against z involves two of these copies, x and x prime. And in this case, we have seen that we have to replace z not by x minus x prime, but by x plus x prime minus x double prime, like minus two independent copies of these guys. So what we get is x dot x plus x prime minus 2 x double prime, and then x dot x minus x prime. This is the first term. Okay, so plus my my now friendly term. I'm happy to see it. And finally, so I do Gaussian integration by parts here as well. So I will have 2 times x dot x minus x prime 2x dot x bar minus x squared plus 2, and this guy I just keep like this. The last guy I just leave at that. Okay. So that's it. That's the and the z square thing we did state it last time. And that's it. That's the end of this supposedly difficult computation, except that now I just have to clean it up. Okay, and this is bookkeeping. So let me do it. I'm going to simplify this expression, just trying to keep track of what's going on. All right, so equals. Okay, so my friendly term outside there, I'm just going to leave aside. And now what? So let's start. So if I expand and I get, if I choose these two terms, yes, this is from the. So in this step, okay. So someone in the chat is asking, how is this term transformed into these two terms? This is from the lemma we saw last time about Gaussian integration by parts. And we saw last time that when we do with z dot some function, let's call it g, everything squared, then this is, as if you're freezing some z plus the expectation of norm of g squared. Okay, and this is the result I'm using here. All right, so now let me do my bookkeeping. So I expand the terms with the blue dots. Okay, so this guy and this guy together, if I expand, I will get x to the power of 4, the norm of x to the power of 4. And I also have some x to the power of 4 that shows up when I select these terms. I have -2 of them. And I also have 1x to the power of 4 when I square this guy. So overall, I have 0 of them. So, okay, that's a good bookkeeping. This one appears 0 times in total. Okay, so now I'm going to focus on the other terms. Okay, so now I can select this guy together with this guy. And I'm going to use Nishimori extensively. So it's going to be -1 time. I'm going to denote it x squared x dot x bar. Okay. So this was pairing this guy with this guy. Now I can pair this guy with this guy, and I will have, it's the same term, but +1 times. So I'm going to write +1 below. Okay, I'm going to have it a couple of times, so I just write the numbers below. So this is +1. Now, what about this term with this term? This is a new form. Okay, this is x dot x prime, everything squared. I'm going to record it separately. So this is -1 times. Oops. Like this. Okay. Now for this guy with this guy, this is x squared, norm of x squared multiplied by x dot x double prime. I can rewrite it as x dot x prime if I want. There's only there's no other copy around. This is again for a term of this form. It appears -2 times. So I'm going to write -2. Okay, and now there's this term with this term. And this is a new form because it's x dot x prime, x dot x double prime. So I'm going to record it as a new term. So plus 2 times expectation of x dot, I can write it like this if I want, x dot x bar, x dot x prime. Okay, so we're done with the first term. Now for the second line, I need to expand this. All right, so I can take this guy with this guy. This is another x square multiplied by x scalar x bar. So I'm going to record 4 times of this guy. Okay. Now, this guy with this guy, we already discussed early, the x to the 4, they disappear. Now, this guy with this guy, this is a term of the form, so it's x dot x prime, x dot x bar. So it's of this form, so it's -4 of this guy. Okay. And now this term, oops, this term with this term, this is again another x square x dot x prime, and I have 2 of them. So I will write +2. And now, okay, now this is over with the second term. And now for the square here, so there's only 2 terms left because we already expanded the x squared to the power of 2, this we already dealt with. So now there's this guy squared, which is going to give me 4 times this guy. And there's the cross product in here, which is going to give me -4 of the first guy. I had erased the +2 of before. Okay, and this I think is the end of my bookkeeping. So I just now need to make my sums. So this is another nice bookkeeping situation because all of these numbers, they sum up to 0. So that's it with this term. And then we have only the 2 guys left over. Okay, so let me rewrite this. We have found that expectation of Hn prime squared is 1/2h expectation of x squared. This is my spurious little guy, which I just carry around. Then 0, then +3 expectation of x dot x bar squared minus 2 times the expectation of x dot x bar x dot x prime. Okay, and what we wanted that this is larger than or equal to this little guy plus expectation of x dot x bar squared. This is what we wanted to complete the argument. And I claim this is all good because by Cauchy-Schwarz, this expectation here is bounded by this expectation. So by Cauchy-Schwarz and the Nishimori property again. Okay, and that's the end of the proof. Okay, so yeah, indeed, as I said, this may be the longest computation we're going to do during this class. So if you're still with me, I'm very happy, and don't worry. Yeah, this is the most let's say compute type of proof that we're going to do. So let me summarize it one more time, just so that we understand the structure. So what we really wanted to show is this approximate Hamilton-Jacobi equation. So we wanted to say that we can control this variance guy by, well, unfortunately, not like in Curie-Weiss, not just the second derivative multiplied by 1/n, but instead this guy plus some fluctuation term. And the way we did it, so okay, we found some convenient proxy. Instead of focusing on x.x bar, we thought maybe it's useful to think first about this guy Hn prime. And okay, the kind of annoying part of the proof was to actually relate the fluctuations of this guy with the fluctuations of this guy. But okay, we can do this. And the perhaps more natural or insightful part of the proof was to argue that we can decompose the variance into these two terms, these two variances. When we let each piece of the randomness fluctuate one at a time, and the first piece of the randomness is responsible for the fluctuation term in the error term we displayed in the main statement. And this piece of the variance is more like standard Curie-Weiss. We get it by differentiating twice the free energy. Okay. So I hope, even though I had to do some bookkeeping, the structure of the argument is relatively clear. Is that we still need to estimate the variance. We decompose it into two pieces, and the two pieces give us these two terms in the statement. All right, so to sum up, we are in position to, we seem to be in good position to use the same strategy as before and apply our convex selection principle. To conclude for the identification of the limit for energy. The only extra ingredient we will have to use compared with our situation for Curie-Weiss is that we need some extra juice to say that this fluctuation term is small. This we didn't have to think about it for Curie-Weiss, but now we do have to think about it. The only new ingredient is that we need is about the fluctuations, the fluctuation term. Which we need to argue is small. Okay, and maybe it's kind of we can be optimistic that this is true, but at least we need to find some way to say it. But in fact, yeah. So what's relatively classical to get is that the fluctuations of the free energy itself are small. Oops. Without the derivative. That's the point I want to stress. And in fact, to be precise, so in the problem set number 9, I give a completely self-contained procedure to obtain the following concentration result. We derive. In fact, you can insert a supremum inside the expectation if you want. That's, let's say, the expectation of the soup over any bounded region, let's say to M of Fn minus Fn bar squared. And this is bounded by, so in the problem set, we get n to the 1/3 because I try to just use the most elementary techniques that we can imagine. This is not the optimal statement, but in practice, we don't care. All I want to know is that it goes to 0 as n goes to infinity. And so there's clearly a difference between saying that the free energy has small fluctuations and saying that the derivatives of the free energy has small fluctuations. But we're kind of used to this sort of problem because it's the same with the second derivative of the free energy. We cannot say the second derivative of the free energy is small everywhere. We can only say it at nice points, or maybe in some average sense or something. So this is part of the difficulty with the problem is that when we display this right-hand side in the statement here, and this was already true for Curie bias. Maybe I have not emphasized it sufficiently, but this term is not true. It's not small in the L infinity norm. If you take the soup of this guy, this is not going to be small. And so, but we got around this by saying we can only, it suffices that we focus on a dense set of points, or maybe even only on these contact points where we touch the function from above. And this allows us to kind of force us to have this quantity be nicely behaved. And we kind of do not look at those places where this is actually large. And the similar thing happens with this term. There will be special points where it's actually big, but we are not afraid because now we have techniques to just handle, get away with the information that this is small at most points. Okay, and the fact that we know Fn has small fluctuations will tell us in some sense that this guy is small at most points. Okay, so in fact, once we are equipped with this extra concentration, oops, sorry about that. Once we're equipped with this extra concentration information about the fluctuations of Fn being small, which I kind of left to problem set number 9. Once we know this, we are not afraid. We are ready to actually do our usual strategy of looking at contact points from above and saying that as n goes to infinity, it must be that this free energy solves the equation at this point. Okay, so that's what I wanted to say today. Thanks a lot for your attention. And as usual, I'm very happy to take questions.